Hello, everyone. My name is Thomas Westnoffer, and this is my presentation on the detonation facility at X Energy Laboratory here at UC Irvine. A quick overview of detonations for those unfamiliar. When you hear the word detonation, you probably think of an explosion, which is correct. Detonations are the driving process behind an explosion. And essentially what you have with the detonation is a combustion in which the flame front is moving at supersonic speed. This is because its reaction front is coupled with a shock wave. Here we have the one-dimensional ZND model named after Zeldovich, von Neumann, and Doring in the 1940s. Looking at the temperature on this graph gives us a basic overview of the structure of a detonation. Here we have our initial temperatures before the detonation hits the reactants. The temperature then jumps across the shock waves, but nothing has been reacted yet here in this zone. Then the reaction front hits it, and the reactants turn into products, and you have your final temperature here. Now, if those scientists were doing work on detonation in the 1940s, what is there to gain from detonation research now? And essentially, we see that as we try to make air and space travel cleaner, more affordable, we need more efficient engines. We're approaching a limit to what current engines can do. Here's a quick example. Looking at this graph, in blue here, we have the thermodynamic cycle of a traditional deflagration engine in which there's a constant pressure across its combustion. However, with these detonations, there's a gain in pressure. And for those familiar with thermodynamics know is that the work done by an engine is represented by the area within its curve for its cycle. And so this jump in pressure creates a larger area, thus more work for the same size engine. So this has led to many detonation engines being proposed. The most famous one would probably be the RDE, or the rotating detonation engine. Here, picture right here, you have an annular chamber, propellants injected axially, and a continuously propagating detonation wave traveling around this to combust your propellants. Now, the issue with this is that it is incredibly difficult to keep this continuously sustained detonation wave, and that is because there's still just not a lot known about detonations. And so at X Energy Lab, we are looking at the fundamental properties of detonations, particularly for their application in these engines. How can we make them propagate more sustainably, and also what properties of them do we need to use in order to size our detonation engines. Here's an overview of our entire setup. I will now look into each individual component, starting with the detonation chamber. This has two sections. We have a larger driver section with a larger cross-sectional area, and then a smaller cross-sectional area testing section. In the driver section, we start our detonation. We have our spark plug on one end that combusts the gases. We have a deflagration and detonation transition device, which is essentially a lattice structure, which causes a lot of shocks to reflect, and that starts the detonation. And then they pass into this testing section, which has a smaller cross-sectional area, which simplifies the detonation to being essentially two-dimensional, which makes it easier for analysis. And this is where all our measurements are going to be taken. Here, we're going to put it in an optical chamber to take optical measurements. In order to make sure that we have the right mass flow rates of gases to ensure we have the right mixture that we're going to be detonating and measuring, we have to set our flow rates. So we have this gas preparation system, which I designed and built myself. And this uses a pressure gauge, a flow control valve, and a sonic nozzle to allow us to set our flow rates. One of the properties of having this sonic nozzle is you have what's called choked flow. And for those unfamiliar with choked flow, the mass flow rate becomes a function of the throat area of your sonic nozzle and the upstream pressure. So by turning this flow control valve and setting the pressure on the pressure gauge, we know what mass flow rate we are getting. Here are some pictures of that. This is some early CAD work that I did, and this was when it was under construction. So gas flows in here. We control with the nozzle with the flow control valve. We can read on the pressure gauge, and then the nozzle would go here. How do we ignite our gases? We use a traditional spark plug. And to build up the voltage necessary for this, we use a bunch of capacitors. So when we press our igniter button, the capacitors charge up until they have the sufficient voltage, and that voltage that discharges and that ignites the gases. So for our optical system, we are going to be taking Schlerin photography, which is a type of optical measurement, which allows you to look at the density differences within your subject rather than just like traditional photography. You get very sensitive images showing you phenomena that you wouldn't see traditionally. So it's like shock waves. Here we have flame. You see all of the differences in the air that you wouldn't really see with traditional photography. So this will allow us to look at detonations and get a better view of their structure and how healthily it is propagating. And this is a traditional setup. Essentially, what we have in ours is a little bit different. So we have constructed this chamber, and we have successfully been able to achieve a detonation. So what's next? Obviously, we're going to integrate this optical chamber, and we'll be able to take our Schlerin imaging. But two of the main questions that we want to ask are, one is, how does heat release affect the detonation structure and what's called the detonation limit, which is basically the range of condition in which this detonation will propagate. And then also, how will introducing carbon nanoparticles affect detonations? So hopefully going forward, we'll be able to experiment and answer these two questions. I am in my final year of undergrad. However, I will be continuing with this research next year, pursuing my PhD, which I am looking forward to very much. And that concludes my presentation. Here are some references. So thank you all for listening.